Welcome to this sailing theory tutorial. My name is Julian. In this video, we're going to be talking about how changes in the true wind velocity and changes in your boat velocity will have an impact on the apparent wind. And we're going to do this with the help of a couple of example problems. Here we have an example where boat speed changes are going to actually have an effect on both the speed and direction of our apparent wind vector. The example reads like this. You are sailing downwind at 5 knots on a broad reach in 20 knots of breeze. As you crest a wave, you pump your sails and surf down the face of the wave at 10 knots. How does this affect your apparent wind? Should you head up, bear off, ease, or trim your sails? So the first thing that we're probably going to want to do is collect the terms that we know. So we know that the true wind on this given day is 20 knots. And let's assume that it's not a gusty day, so it's a constant 20 knots. We know that we have two boat winds. Boat wind 1 is 5 knots, and boat wind 2, it went up to 10 knots when we started surfing. Okay, the question's basically asking us, what is apparent wind 1? And also, how does it change when we get to apparent wind 2? So to solve this, I think we just need to draw a couple diagrams and talk about it. First thing I'm going to do, like always, is put my wind up at the top of the page. And we didn't decide on our directions here, so I'm going to draw my boat heading on a broad reach, something like this. And so what that means for me is that my boat wind is going to be pointing up in this direction here. So I'm going to take that, and I'm going to take advantage of my copy paste, and I'm just going to stick it in next to both of these boat winds. And the true wind, because I drew this arrow here straight down, true wind's coming straight down the page. So why don't we make diagram number 1 with our 5-knot boat wind? So for diagram number 1, we're going to say that we have 5 knots of boat wind, about that long, and it's pointed straight at the bow of the boat, BW1. We know, of course, that 20 knots of true wind is blowing straight down the page, so that's 5, 10, 15, 20 knots of true wind blowing straight down the page. I'm going to draw that again as an unbroken line. 1, 2, 3, 4. That's the true wind. And so what we're going to see for ourselves is that apparent wind 1 is the connection between the tail of the true wind and the tip of the boat wind. That's TW1. Oh. AW1. Okay, so to make our second diagram, just to keep all the directions pointing in the same direction, I'm going to make a copy of this diagram here, and I'm going to paste it down here. So we know that the apparent wind is going to change, so I'm just going to delete it. The true wind, of course, is going to stay the same, but to keep our diagram synced up, I need to move it out of the way for a minute. And now, what do we know about the boat wind? Well, our new boat wind is going to be 10 knots, which just by coincidence is twice as much as the first boat wind. So I'm again going to take advantage of that, and I'm going to make a copy of the boat wind, and I'm going to paste it right there. This way we're keeping our directions and our scale the same. And I'm just going to try and clean this up. Nope. Okay, so we'll call that boat wind 2. Now we can move our true wind back in. And now that we've done that, we have the opportunity to draw our second apparent wind vector. So this one's going to be AW2. So what do we see happening between AW1 and AW2? We see two things. One, it's shorter, so the magnitude is smaller. which means less wind. And 2, this is an important second note, it's shifted or rotated. And the direction that we would say it rotated is clockwise or forward. Where do we get forward from? Well, we get forward from the idea that this end here has moved towards the bow of the boat. Forward. So, to answer that first part of the question, what does this do to your apparent wind? It shortens it, and it shifts it forwards. Now, to answer the second part of the question, we actually have to do a little bit more thinking. Should you head up, bear off, ease, or trim your sails? So we have a couple of options here. So let's talk about our sail trim. So we're sailing downwind, and our apparent wind is coming from a certain direction this way. And all of a sudden, it shifts forwards. So we have a couple of options. We can let our sail out, we can pull our sail in, or we can leave our sail exactly where it is. Now, I'm going to suggest to you that probably we shouldn't leave it exactly where it is, because the direction of the wind just changed. So the question is, do we let it out or pull it in? And as a general rule, if the wind has shifted forwards, that's like a knock. And so if you have a knock, then you're going to sheet in. So option 1 then is sheet in. And it gets a check mark. Okay? Out gets an X. So then our other options are to head up or bear off. And it's just the same thing. So the wind shifted forward. Is that a lift or a knock? Well, in this case, it's a knock. So we can head up or bear off. I'm going to put an X against heading up, because if you head up on a knock, you're just going to make your sails even worse trimmed. So we can bear off. So our options are sheet in or bear off. And now I just want you to think for a second, if you were racing, what would actually be the right thing to do. So we're trying to get to a mark that's down here, for instance. Would it be a better idea to sheet in and go faster, or bear off and head towards the mark? Well, that's a decision you have to make for yourself, but I would be erring on this side right here. So here we have part B of this example, and it says sailing close hauled in the same conditions as part A. In the trough of a wave, you stuff your bow into the next wave and slow down to 2 knots. How does this affect your apparent wind? So we've got 2 different things going on. 1, we're on a different point of sail, and 2, we're slowing down instead of speeding up. So let's scroll down and see what happens. Again, we're going to collect our terms. And same conditions as A, so our initial boat speed is going to be 5 knots. And boat wind 2, we just found out, is 2 knots. Now, what's the direction of that? Let's just draw a quick little sketch here. We got the wind coming down. We got a boat heading upwind, close hauled, and that's going to be our direction for our boat wind. Is going to be down and to the left. So just like we did for the last question, let's draw 2 diagrams. So diagram 1, start with the wind at the top, and we'll start with a boat heading up the screen with sails trimmed in. First wind we're going to draw is the boat wind, and we're going to anchor it on the tip of the bow there. And we'll make it 5 knots long. Okay, so that's a 5 knot boat wind 1. We have 20 knots worth of true wind to draw here, and it's only just barely going to fit. 5, 10, 15, 20. Call that the true wind. And the last thing we're going to draw is the apparent wind, and we're going to connect it from the tail of the true wind to the tip of the boat wind. And that'll be the apparent wind number 1. So that's diagram 1. Now, again, just so that we keep our directions in our scale the same, I just want to copy diagram 1 and put it below for diagram 2. And we're going to see what happens here. When we erase boat wind 1 and the apparent wind, so we're going to draw in our boat wind, and it's pointing in the same direction, but it's 2, not 5, so it's going to be a very, very short arrow here. To that, we're going to add the same true wind that we added before, so that's 1, 2, 3, 4 is 20 knots. And what we're going to see happen with the apparent wind, hopefully, is that it's shortened a little bit, and it's rotated. So which way is it rotated? Let's take a look. I'm going to take this apparent wind vector, and I'm going to copy it and paste it over here. And just because it's vector number 2, I'm going to make it a different color. I'm going to take apparent wind vector number 1, and I'm going to copy it, and I'm going to try and place them side by side. So what happened? Well, we have a rotation going on, and the rotation was in this direction, or if we wanted to line them up tip to tip, then we would see actually that the rotation is going to be in the same direction, but this way, which is basically a rotation aft or back. So one of the effects is that the magnitude decreased, and the other effect was that we got basically a lift. Or the wind rotated back. So the last thing I want to do then is fill in this table that's going to show how the apparent wind speed and direction changes with changes in boat speed. And we've basically solved the problem with part A and B of the example, and we can use that to fill this table in. So upwind, when the boat speed decreases, we just did this example, what did we see to our apparent wind speed? Well, if the boat speed decreases, then the apparent wind speed also decreases when we go upwind. Now, what else did we see? When we're going upwind, the apparent wind direction, we just saw that it shifts aft. Which is essentially a lift. So, what can we infer from both of these things? Well, basically we can infer that in this column over here we're going to have the opposite. So the apparent wind speed is going to increase, and the apparent wind direction is going to shift forward. And that's going to be a knock. So that's interesting. Now I want to scroll down, and we're going to talk about what happens when you're going downwind. And again, we just did this example. We're headed downwind, and we do something that makes our boat speed increase. Maybe we pop up on a wave and surf. What happens to our apparent wind speed? Well, we just saw something interesting. We saw that it actually decreases. And that's because the vectors are adding in a direction that cancels each other out. Now, what else did we see? Well, we saw in the apparent wind direction that we got knocked when we increased the boat speed. So that's a shift forward, or a knock. So what does that mean? That means that the direction change is the same whether we're going upwind or downwind, but the effect on the speed or magnitude of the vector is not the same whether we're going upwind and downwind. And again, we can fill in this. So you can infer that then this is going to increase with a decrease in boat speed, and that the direction is going to shift backwards, which is going to be a lift. So again, in general, the direction change is the same whether you're going upwind or downwind when you change the boat speed, but the magnitude of the apparent wind velocity vector is opposite whether you're going upwind or downwind. And you can try to prove these columns here for yourself if you want, just by reversing the example and drawing the diagrams. In this example, we're dealing with gusts and lulls, which means we're dealing with changes in the true wind speed. The example reads, you are sailing upwind on a close-hauled course at 5 knots in a mean wind speed of 15 knots. Part A of the question asks, what happens to your apparent wind when a 5-knot gust hits? So we're going to solve this the same way that we solved the last example, and we're going to draw diagrams. First, we need to collect what we know. So we know that we have an initial true wind speed, which is equal to 15 knots. We know that we have a second true wind speed after the gust hits, which is 5 knots greater, so that's 20 knots. For this question, we're assuming that the boat hasn't had time to accelerate after the gust hits, so we only have one boat wind to deal with, and that's going to be 5 knots. And the things that we're looking for are, what is apparent wind 1 doing? What is apparent wind 2 doing? And of course, what's the difference between the two of them? So let's start drawing our diagram. We'll start by drawing a boat on a close-hauled course. And I'm just going to move that boat down a little bit. Because we have the same boat wind for both boats, I'm going to draw the boat wind right now as 5 knots first, and then I'm going to copy it so that we can work on both diagrams at the same time. So just to label it, here we have before gust, and here we have after the gust. Now, we know that before the gust, our true wind speed, which is blowing straight down the page, is 15 knots. So let's draw that now. 1, 2, 3. That's 15 knots. And we know that after the gust hits, we have 20 knots. So we'll draw that one as well. 1, 2, 3, 4. So that would be TW2. And then to draw our apparent wind, we're going to do the same thing we always do. We're going to connect the tail of the true wind to the tip of the boat wind. So there's apparent wind 1, and we'll draw apparent wind 2 over here. So, what's the difference? Well, first of all, we can say that this one is bigger in terms of its magnitude. And secondly, we can say that there was an angle change, but it's really hard to see what the angle change was. So I'll just copy the arrow here. We'll move it over to the side, and we'll see if we can tell which way the arrow's turned. So here we can see that the difference in the arrows is a rotation in the aft direction. And like we said in our first example, a rotation in the aft or backwards direction is the same as a lift. And that's why when a gust hits, you can head up. So now the question is, what happens to your apparent wind when a 5-knot lull hits? And it's going to be basically the opposite. So let's write that out. True wind 1 is equal to 15 knots. True wind 2 is equal to 10 knots. Remembering that the wind is blowing straight down the page. The boat wind, just like in the previous example, is going to be 5 knots. And we're going to assume that because we're still on close hauled, the boat wind is blowing back in this direction. So, we'll start by drawing our boat. We'll add the boat wind in. And just like before, I'm going to copy it so that we can work on both diagrams at the same time. Now in this case, we have a true wind that starts at 15. 1, 2, 3, 15. And in this case, we have a true wind that starts, or that is only 10. So that's 1, 2 is 10. I'm going to connect them to show our apparent wind vectors. And we can see what the difference is between the two vectors. So, first of all, apparent wind 2 is much smaller in magnitude. And second of all, there was a rotation again. So what I'll do is I'm going to copy apparent wind 2, and we'll see if we can tell which way the rotation went. So if I line apparent wind 2 up right there, we can clearly see that there was a small rotation in the forward direction. And like we said with the previous example, a rotation in the forward direction is equivalent to a knock. And that's why when you sail into a lull, you often have to bear off. Part C of this example asks us to repeat A and B for a boat sailing on a broad reach. So let's get to it. We have the wind coming from the top of the page. We have 3 true winds to consider. So this is going to be before a gust or lull. This is going to be after a gust hits, and this is going to be after a lull hits. Of course, we're still assuming that we have a constant boat speed of 5 knots, and I think you can see where this is going. So we have a boat here sailing on a broad reach. The boat wind is then blowing up towards the bow of the boat. In our initial case, we have a 15 knot true wind, so that's going to be 1, 2, 3 is 15 knots. And now I'm going to copy that twice for our second and third true wind. Our second true wind is just a longer true wind. So I'll draw this at 20. 1, 2, 3, 4 is 20. And we can get our apparent wind from that. Now our third true wind is actually shorter. So I'm going to draw it as 10. 1, 2 is 10. And there's apparent wind 3. And of course here is apparent wind 2. So let's see if I can copy those arrows and we'll see which way they go. That was apparent wind 1. So down here we have apparent wind number 1 in yellow. I'm going to copy apparent wind number 2 and make it red. And if we line that up tip to tip, we can see the direction that the apparent wind is shifted. Now I'm going to take the third apparent wind and I'm going to copy it, and I'll make it green. So if I move that one in, we should see a pretty dramatic change in the direction. So what does this tell us? This tells us that when we're sailing downwind, if a gust hits, we're going to see a rotation aft, which is equivalent to a lift, and if a lull hits, we're going to see a rotation forward, which is equivalent to a knock. So to finish this example, and actually the whole video off, what I want to do is just fill in this table the way that we did for the last example. So I have a table for upwind sailing and a table for downwind sailing, and I want to map the true wind changes with gusts and lulls to changes in both apparent wind speed and apparent wind direction. So when we're sailing upwind and we encounter a gust, we're going to notice that the apparent wind speed also increases. We proved that in the example. So when we hit a lull, we're going to see a decrease. Now when we're sailing upwind and we get a gust, what we see is that the apparent wind direction actually shifts aft. And this is the same as getting a lift, or a velocity lift in this case. Now when we sail into a lull, we see the opposite. The wind shifts forward, which is the same as saying that we get a knock. When we're sailing downwind and we hit a gust, we should see that the apparent wind speed also increases. When we're sailing downwind and we hit a lull, we should see that the apparent wind decreases. Now when it comes to the wind directions, if we're sailing downwind and we get into a gust, like we saw with the last question, in a gust, the wind shifts aft, which is the same as saying that we get a lift. And conversely, when we sail into a lull going downwind, the apparent wind shifts forward. And that's the same as getting a knock. So what you can see is that when we're dealing with changes in the true wind, or gusts and lulls, the table that we made for upwind sailing is the same as the table that we made for downwind sailing. And this is the exact opposite of the table that we made when we were dealing with changes in boat speed. You can see here that the apparent wind speed column changes from upwind sailing to downwind sailing. Now, if you have any trouble keeping that straight in your head, I would recommend that the easiest thing to do is just draw the vectors every time you need to answer a question on it. Or, if you're trying to think about it, think about the direction of the arrows. If the arrows are pointed in the same direction, you're going to end up with an increase in speed. But if the arrows are pointed towards each other, you end up with a decrease in speed. This concludes my sailing theory tutorial. I hope that you've seen how changes in the magnitude of both the true wind vector and the boat wind vector have an impact on the direction and the magnitude of the apparent wind vector. In my next video, I'm going to be talking about how sails actually work, and I'm going to show you how to visualize the flow over a sail by drawing a diagram with streamlines. Thanks for watching.